can you talk a little bit about some of the features that we are seeing on the lunar surface here?
Yeah, absolutely. So if you look on the moon right now to the left middle area of the moon there, the bright spot that you see there, that's Copernicus crater. The dark region that is sort of like right in front in the middle center of the moon right now, that's the Imbrium basin. And so these are impact features that we have on the moon. So when the moon formed throughout its history, over its 4.5 billion years, has been bombarded by meteorites and asteroids. And for the Imbrium, that's the darker round area that you can see there, what happened is there's a massive crater, and so we call these a basin, and melt from the interior of the moon came up through cracks and then filled that basin crater. And you can imagine that as a big lava lake, and then it cooled to form basalt. The same thing happens at the moment on Earth. Hawaii is erupting, and that brings up basalt from the interior of Earth. So these basalt samples, when we analyze them and we look at these, we can learn something about the interior of the moon. I see that we lost our actual live view, but in this beautiful view that we can see here, you can really nicely see Copernicus right in the center, and that's brighter because it excavates crustal material, which is white or bright, compared to the mare, which are basalt, which is dark. Oh, there we are back. So Copernicus is now in the lower right corner of that image. That's a fairly young crater, and that's why it still appears fairly bright, because over time, when the sun interacts with lunar rocks, it darkens over time. So we call that space weathering. Yeah.
And so we are flying fairly close to some of the Apollo landing sites now. We're a little too high above. We're about 2,000 miles away from the moon still to make out any features. But can you talk about a little bit about what the Apollo program studied in those landing zones, and maybe touch on how Artemis is going to be different, because we're going to be landing in an entirely different spot, right?
Yeah, absolutely. Apollo wasn't so much about science. It was more about like, hey, we're actually going to the moon and we can do it, and like the technology to show that we can do it. Apollo 14 and 12 sort of landed near Copernicus, like south of where Copernicus crater is right now that I pointed out in that region. And so Apollo 14 landed there in 1971, right above the Framora region, which is kind of like south of Copernicus, and it's right at the edge of that big Imbrium basin that I talked about. They brought back a lot of rocks. They were interested in the rocks that were excavated from Imbrium. So there's a lot of impact melt, so we call them, or breccias. And every time a rock gets exposed to like heat and pressure and started to remelt in like an impact event like that, it resets the internal clock. So when rocks form, they record the condition from which they formed, including the age, like the time when they formed. But every time there's an impact event and it gets remelted, that internal clock resets. Now we can take these rocks and then measure the ages of them. And so every time the clock got reset, we now have the age of that impact event. And so we want to know when Imbrium formed, because it's such a big event that happened on the moon, that we can put everything else in relative age to each other. So that why that mission was important. Apollo 12 landed in the Oceanus Procellarum region, which is sort of to the lower left and then going up. It's kind of like where that shaded, like where you kind of stop seeing the moon, you know, the boundary of the shade and the sunlight lit area. The little bright spot that comes up on the, what is that, lower left third of the moon, that is Aristarchus crater. So that's a super bright crater in that Procellarum region, which we're now seeing more and more of. So that's sort of the area where Apollo 12 landed. That landing was to sort of show that we can do a pinpoint landing. So they landed 200 meters away from the Surveyor 3 lander, and they actually brought a piece from Surveyor 3 back to Earth to like really show. And that then paved the way for future missions to like really like, hey, we can do a pinpoint landing. So we can go to like a more difficult terrain where we can land, where it's more ruggedy. And so that's where we went there. And so now you can see even more of the Procellarum region. Most of that is dark gray, as you can see, and so these are the basalts, and that mission brought back a lot of these basaltic materials. And then we can look at the ages, and it turns out that those basalts were very different, and they were younger than the Apollo 11 mission, than the rocks that they brought back, the basalts that they brought back. Now, Artemis is going to be super exciting because we're going to a very different region. So if you look at the surface here, and you can see that's mostly dark gray, so it's mostly basalts. You can see in the upper part of the moon that's still bright. That's what we call the highland crust. So that's the very old crust. So when the moon formed, there was a giant impact between two protoplanets. It collided, created a lot of heat, everything melted. The center part formed and became Earth. And then the debris cloud that surrounded it coalesced and then became the moon. So once upon a time, the moon was covered in a global magma ocean. So it was fully molten, right? And if you have a global magma ocean, you start crystallizing things. So now when you crystallize stuff that is denser than the melt, that sinks, right? And if you crystallize things that are less dense than the melt, that starts to float, like ice is floating on water, right? And so now we have these crystals crystallizing these minerals, and they are less dense, so they float to the surface and they build the crust. These crystals are called plagioclase. They're white. And so your crust that then forms on the moon is white. And that's why the moon looks so bright when you look at this image or in the night sky, because that's the old crust of, the oldest rocks we have, and they're white in color. And so that's why this is so bright. Now the near side, so the side that we see right now, we see these dark patches, which then are the younger basalts that came to the surface once you start impacting it, and you take stuff away, you made these big basins, and then the interior remelts, and that melt comes up to form to fill these craters. That's very special. So it turns out that this Procellarum region, where Imbrium sits in, where Apollo 12 landed, where Apollo 14 landed, all these rocks that were brought back, they have a weird component that we call creep. And it's spelled K-R-E-E-P, and it stands for potassium, rare earth elements, and phosphor. That entire martyr regions that you can see here also has iron in it, lots of iron and lots of titanium, but the rest of the moon doesn't really have that. And so geologically speaking, all the Apollo rocks are really, really cool because they're very special, right? So if I would give you 6 missions and you land them on Earth and you land them all in Yellowstone National Park, and you collect all your rocks, right? You get, geologically speaking, really interesting rocks, but they're not representative for the United States or the rest of the world, right? So same happens with Apollo. Really cool rocks, geologically speaking, very interesting, lots of basalts, right? They all have this weird creep component, so they're all creepy. But the rest of the moon is very different, so they're not representative. Now with Artemis, we're going to go to the South Polar region. So that region is more representative compared to Apollo. We don't really expect a lot of basalts there, so that's more like highland region. The South Polar region also has the largest impact basin that we have on the moon, and also the oldest. So if we can bring back rocks from there, we can hopefully date that really, really old impact region, and then get a better idea of when things happened on the moon and establish a timeline. Now we also know that the polar regions are really, really cold. And so ices or volatiles and gases on the moon, they freeze out in the polar region. So when we go there and collect rocks, we can also bring back these frozen samples and then learn something about where the water is coming from, whether it's moon or, there was lots of asteroids and comets that impacted the moon. And then so we can also learn about something about the water that was delivered to the Earth-Moon system, which most likely also ended up on Earth. And so we can learn something about our own history and how the moon formed and evolved over time better than we can with Apollo. We're missing a lot of rocks and processes with Apollo, and hopefully we can fill these gaps with Artemis.
You are a wealth of knowledge. Thank you so much for sharing all of that information. Now, as we continue to get closer and closer to the lunar surface, of course, these features are going to become more and more clear. Orion is now 2,000 miles away from the moon, but at closest approach today, it will be just about 80 miles above the lunar surface. So before you go for the day, it looks like we are starting to get some better views of that area that you were discussing before. Is there any other items or areas that have come into view since we've been chit-chatting that you think would be helpful to point out?
Yeah, so we see Kepler crater, which is sort of to the left and lower left of Copernicus, what I just pointed out. So it's this like grayish area with the little dot in the center. And then if you go from there further to the left, right at where the moon's shades are, so there's still a little lower left, that really bright area, that's Aristarchus crater. And that's a really young crater, and it's really bright because it brought up material from that crust that I said, and that's this white rock. It turns out we have orbital reflectance data. So when we look at the light, the sunlight that gets reflected off the surface, we can make assumptions about the chemistry in that region. And it turns out that that region is, geologically speaking, really, really complicated. So it brought back up old crustal material, but we also see some basaltic material. And in the central peak, we see material that is silicic, so it's really, really high in silica. And that usually means there's some kind of evolved rock. And when we say evolved, on Earth, that usually means like granites and stuff like that. We don't really mean it that way here, but it has more silica content in it. When I say central peak, so what happens when you have a big impact into the crust rebounds and brings a central part comes up. If you think about it, throwing a rock into water, right, it makes a splash, and then the water rebounds and brings a kind of like a central thing up and then plops back down. So if you would freeze that water, it would stand up in the center. So that happens on the moon or on Earth as well, where like the crust rebounds. And so the central peak is the area that is the deepest material that got brought back to the surface. So that is of importance and special interest to scientists, because now we have another window into the interior of the moon to study these things. And it turns out, specifically for that little bright crater there, it's super complicated, and then we're still trying to figure out what we are seeing.
So it sounds like there's definitely much to be learned from the moon, especially through the Artemis program, and I'm sure you're looking forward to getting some of those samples back to be able to study in depth.
Oh, absolutely.
Well, thank you so much, Juliana, for taking time out of your day to chat with us. I really appreciate it. I hope you have a good rest of your day.
Thank you so much, and thank you for having me. This is fantastic.
We're now 50 minutes away from today's return-powered flyby burn. This burn will slingshot Orion around the lunar surface and put it in a trajectory ahead of a splashdown on December 11th back on Earth. This burn will be a 3-minute and 27-second long burn and will be the longest burn of the mission utilizing the Orbital Maneuvering System, or OMS engine. You are getting a view of the OMS engine on your screen. It's in the very top left, the largest engine on your screen. The next major milestone that we're tracking here in Mission Control Houston is the Go, No-Go poll. During this poll, NASA Flight Director Judd Freeling will go around the room and poll each of the flight console positions to ensure that all is looking good ahead of today's burn. Orion is now less than 2,000 miles away from the moon, 1,756 miles, moving at a velocity of 4,563 miles per hour. At this time, Orion is over 237,000 miles away from Earth. And if you're just joining us, Orion is now 1,550 miles away from the moon. We are anticipating today's return powered flyby burn to begin 43 minutes from now. This burn will last 3 minutes and 27 seconds. During the time period that the burn takes place, Orion will be in a loss of signal period because it will be directly behind the moon, and the moon will be blocking the signal with the deep space network. Today's loss of signal will last for 30 minutes. After we come back around to the other side of the moon, we anticipate regaining communications with the Orion spacecraft, and that's when the team here in Mission Control will be able to analyze the return-powered flyby burn and make sure everything went as expected. This burn is critical as we look ahead to a return and splashdown of the Orion spacecraft on December 11th. Today's burn will put us in a trajectory